Alright folks, so I am going to be taking a look at the 2010 fall exam from UNB for their 1003 course. So I'm just going to go through it. I'm going to try to do very brief chatting about the questions as I do it. This is mainly what I'd like you to do is if you would like to not watch this video, go and download if you go just in a normal search engine, just put in old exams UNB math or something along those lines. This is the 1003 course, so we'll call it 1003 and fall 2010 version. So they have it readily available on there. Just to give you an idea, there's 100 marks worth of material here, and you are given, according to this, 5 minutes short of 3 hours. Not sure why 5 minutes short, but 1, 2, 3, here we go. So for the first one here, the way that it's set up, it says use the rules of differentiation to complete the derivatives of the following functions. Do not simplify the answers. So in A, we're told that y is equal to y to the 6th minus 3 over the square root of x plus 5 over x squared minus 2. So it's a pretty easy to deal with function. We have 4 different terms, all of which can be simplified a little bit. I guess not all of them. The first one's good, is x to the 6th. I see a lot of students take a look at that second term and the third term and think quotient rule. It works, but it'd be a little bit easier if you just saw it as a straight power rule, in my opinion. So just to make it more clear as to what I'm going to do with those in terms of a power rule, I will write the x's that are currently in the denominator as negative exponents, so reciprocals, as well as the appropriate square root 1/2 power and then the square for the power of 2. All right, well, I'll go ahead and actually take the derivative now. So y prime is equal to 6x to the 5th plus 3 over 2 x to the negative 3 over 2 minus 10x to the negative 3 and then plus 0 there at the end. So that's all I'm going to do here. And it says that we do not need to simplify. So I'll leave it at that. Next up, we have for 1b, we're given that y is equal to e to the 2x over 1 minus e to the x squared. All right, so there's not really anything meaningful I can do here, I don't think, in terms of simplification to start with. So I'm going to go right into quotient rule. So low, d high, there's a chain rule there, so times the derivative of the inside, minus high, d low, so derivative of 1 is 0, and then negative, and then derivative of e to the x squared is e to the x squared times the derivative of the inside, which kicks out an extra 2x there for the chain rule. So low d high minus high d low all over the denominator squared. And so it says not to simplify, so I just shouldn't touch it. We'll leave it at that and continue. Next one, g of t is equal to ln of the cosine of t minus sine of the ln of t. So I'm doing these as I go. If I make any mistakes, email me, let me know, and I'll see if I can recut that into it. So I'm going to try to do this particular setting as a single cut because I'm at school and the laptop stinks at trying to edit video. It takes me long enough at home and my desktop's pretty reasonable. So I'm going to attempt to just do it as a one-shot and hope that I can go through a 3-hour first-year university exam without making I was gonna say a mistake, but that would be really pretty borderline for me. So we'll see. All right, so the derivative of the natural log is going to be 1 over whatever's inside times the derivative of the inside, which is negative sine of t. And it can be written as a single fraction, a little tidier, and I wouldn't take up as much space there. And then minus the derivative of sine's cos, leave the inside alone, times the derivative of the inside, which is 1 over t. Again, I could write it as maybe a single fraction there, and that would look nice. But that's all right. We don't have to simplify. So that's all there is to this one. I think it's just a couple of chain rules. Yeah, it's just making sure that that was written down correct originally. Okay, so moving on. Question 4, or well, 1D, I guess. So 1D. Let's see here. This is given as y is equal to the arcsine. In class for you folks, I usually don't write arcsine. That being said, it does actually list both of the ways here on this exam. It writes arcsine, and then it says in brackets, i.e. sine to the -1 of 2 over x. This is going to be a little bit more painful for me. So it's trying to think. So it's going to be 1 over. Ooh. No, 2 over x squared, leave the inside alone, times the derivative of the inside, which that inside part up here, let's just write that in. It's the same thing as 2x to the -1. So 2x to the -1, when we do the derivative of that, it's going to be -2x to the -2. Now, the only thing is, I have to remember whether the arcsine is, I'm going to do a little fiddly thing off to the side. It's a waste of time, but that's okay, because I actually haven't done any inverse trig derivatives for a little bit. So y is equal to the arcsine of x, which means that the sine of y is equal to x. And going from there, we'd have cosine y prime is equal to x, and so you get y prime is equal to x over the cosine of so the derivative of y, cosine leave, oh sorry, it's equal to derivative of the other side is 1. So 1 over the cosine of y, and the cosine of y, since sine of y is opposite over hypotenuse, and it gives you x, that's x over 1, which means this thing down here would be this squared minus that squared underneath the square root. So square root of 1 minus x squared, and so it is positive. Yeah, I just wanted to make sure. I did get it right, but I wasn't, I was feeling a little bit wobbly on which one of the arcsine or arc cosine was the negative value. All right, so that's good, I think, and I will move along to the next one. The next one is actually a logarithmic differentiation. So we are going to say x plus 1 to the power of 1 minus x. And for this particular one, I'll take the natural log. I love natural log over the other options. Just has a tidier derivative, so you might as well. So it looks something like this, and technically if you're worried about it, this is all inside of the logarithm, but it should be interpreted that way, the way it was written anyway. All right, so the whole purpose of doing this is so that we can use the logarithm rule that allows you to take exponents on something inside of a logarithm and write them down front as coefficients instead. So we have that coefficient written as a multiplication to the rest of that logarithm. So now we have a product rule on the right hand side. Before, you actually had a variable base and a variable exponent, which is none of the rules that we have. So we changed the way that it looks, and it is now a product rule. And so on the left hand side, it is implicit differentiation, so we're taking a derivative with respect to x of something that's written in y. So it's 1 over, leave the inside alone, times the derivative of the inside, which is going to be y prime or dy by dx. That's going to be equal to product rule on this part. So I'm going to leave the first part alone, multiply by the derivative of the second part. So the derivative of the second part is 1 over that inside times the derivative of the inside, which is just 1. So that's the first part of product rule. And then I'm going to take the derivative of this, which is -1, times this part left alone, which is ln of x plus 1. And so again, I guess I should rearrange it at least for y prime. So y prime is equal to y, which is the original x plus 1 to the power of 1 minus x. That's what the y was here, and multiply back up onto the other side, times the rest of this stuff here, which I will take the time to write down, 1 minus x over x plus 1 minus ln of x plus 1. All right, so that is question 1. It is 5 different parts, each of them worth 4 points. So technically we're done 20 marks out of the 100 on the exam. It's probably going to be the easiest 20 marks there, so won't necessarily keep going at this pace, but that's okay. We'll go from there. And that's not to say I didn't mess something up. So again, if I did, let me know. Question 2. And this one is actually asking us to differentiate, use derivative rules, but simplify your answers. So we're going to be asked to make sure things are a little bit tidier in the end. Now, I say in the end, but probably the easiest way to make sure that things are tidy in the end sometimes is to make sure things are tidy up front. I can't do anything here in particular, so I'm just going to go right to it. So that is a product rule for the first part, x inverse tan. So that would be, I'm going to take the derivative of the first part, which is 1, and then the derivative of the second part is, I'll leave the second part alone, so my apologies. 1 times, and then you just leave the inverse tan of x over 2. And then I have to do the second part of my product rule, which is going to be plus x times the derivative of the inverse tan function, which is 1 over 1 plus x squared, but it's actually 1 over 1 plus the argument squared, which in this case is the x over 2. I'll multiply it right into the x that's already there, so it's 1 over 1 plus x over 2 all squared, times the x, so that's why there's an x in the numerator, times the derivative of the inside, because we're in the middle of doing a chain rule right now, so I get an extra 1/2 kicking around there. I also have, we're running out of room here. Did I give? I didn't do it as well as I could have. Let me, sorry for making this look a little funky, but.
Can I have a custodian to the main office, please?
Oh, I'm at school. Forget all that entails sometimes. All right, so give myself a little more room, and then minus the logarithm, natural logarithm of that, which is 1 over the argument times the derivative of the inside, which is actually 2x up top, and I'm going to multiply the 2x into the one that's already there, just to make it a little shorter and hopefully fit on the screen a little better. All right, so at this point, I'm hoping that this thing over here looks like it could suspiciously tidy up a fair bit. So I'm going to hope that that's the case. This part doesn't look like anything will happen to it. Inverse tan of x over 2. There's no other inverse trig function, so it's not looking promising. In this part, though, I'm going to say that it's the 1/2 that's there, and then x over 1 plus x squared over 4. So I'm going to say 4 plus x squared over 4 in the denominator. So I squared out the second part, and then I gave it a common denominator, so it's 4 over 4 plus x squared over 4, which gives me 4 plus x squared over 4, which is actually this part right here is the same thing as this part right here. So that's looking pretty good. I'm going to turn this into a single, nicer looking fraction. The second part over here is pretty good the way that it is. It doesn't look like you can really do a whole lot to it. I guess I'll write down the whole thing again. So it's inverse tan of x over 2. And then here, multiplying by the reciprocal. So it's x over 2, I guess, if we kind of look at this part right here. X over 2 times the reciprocal of that, which is going to give me the multiplied by 4 up top divided by 2. So it's 2 x over, I'm going to write it the other way so it matches the other one. So it's x squared plus 4 minus 2x over x squared plus 4. Look at that. They're really kind, I guess. Or maybe not kind, but it ends up that those two terms end up being identical. So we're left with, in the end, just that the answer is the inverse tan of x over 2, which is cool. Tidies up really, really nicely. Unexpectedly, from my point of view, when I first look at the question, I don't know that that's going to happen, but that's okay. Cool. Next up, so we get 2b. So this one is written in terms of theta. It doesn't really matter, but theta of ln of secant squared of theta. All right, so let me give myself a little more room. G prime of theta is equal to, so natural logarithm again. We've done a lot of natural logarithm derivatives. Not that I will complain, because I like them. They're pretty tidy. So 1 over secant squared x. Now, I'm going to make a little side note here, because if you don't remember, the square in this position right here is the same thing as the entire reciprocal trig function, which is secant, being squared. So the position of that square, it's really nice and tidy in this notation, the first one that you see there, but it's the same as that one. And in this notation, it might be hard to note that the working from the outside to the inside, it's the natural logarithm, and then actually the square. So when I go to do the derivative here, I'm actually paying attention to that square part next, because I'm doing the, right now, because I've probably lost track of where I am, I'm doing derivative of the outside part, which is my natural logarithm, 1 over, leave the inside alone. It's chain rule, so it's times the derivative of the inside. But the inside is actually a secant inside of a square. So I actually want to use power rule next. So the 2 comes down, I leave the inside alone, now to the power of 1, which I don't need to write in there, times the derivative of the inside. And the derivative of secant is actually secant tan. So we would get, in this case, the secants look like they're going to cancel. So we get secant squared up top, secant squared down bottom. And in the end, it looks like it's just going to be 2 tan theta, which again is it's pretty nice compared to what we started with there. So our derivative in 2b, I believe, is 2 tan theta. All right, lastly, we are going to look at 2c, which is set up as p of x is equal to the square root of x squared plus x over x squared. Okay, so I'm a big fan of trying to simplify things before you get started, if you can. And I think, from an algebraic point of view, that this is going to be simpler to take the derivative of. So I said that you could divide both of the pieces in the numerator there by the x squared. So there'd be x squared divided by x squared is 1, and then x divided by x squared is 1 over x, which is the same thing as x to the minus 1. Bare minimum, you could make it x plus 1 over x if you still want to keep kind of the, you don't want to get the negative exponents involved there. Oh, that's unfortunate, I dropped the whole thing. All right, we'll pick it up in a second. So let's go ahead and try this one out. So that's going to be the derivative is equal to 1/2, leave the inside alone, now to the power of -1/2 times the derivative of the inside, which is going to be, I'm going to write it at 0, plus, but it's minus because the -1 comes down, x now to the power of -2 because we subtract 1 from the exponent. So this is going to be equal to 1/2 square root of 1 plus x to the -1, and then times negative x to the -2, which is the same thing as an x squared down here. I don't know what kind of simplifying they necessarily want. I'll go a little bit further. So -1/2, and I'm going to put the x squared on the inside, I guess. So it becomes x to the 4 plus, and then the next one would be x to the 4 times x to the -1 would be x to the 3. Really tempted to take the time to try that one in Desmos and see, because I don't feel quite as good about that necessarily. So let's do that. So I'll show you how to, if you're rusty on it, how to check your derivatives using Desmos. So if I were to, I'll load up Desmos and then I'll pop it over there for you. All right, so in this particular case, we started out in the beginning with p of x is equal to, and I'll write it exactly the way that it is, so I won't tidy it up like I did. So it's x squared, x squared plus x over x squared. All right, so that's what we have to start with. Desmos is pretty smart, so I can say p prime of x, and it will give me the derivative there that it thinks that it is. And then what I need to do is, I'm just going to pop this up for a second because I can't remember. -1/2 times the square root of x to the 4, x to the 3. Okay, so, all right, over here. -1/2 times the square root of x to the 4 plus x to the 3, I think. I'm going to just double check, but that looks pretty promising the way it's set up. Yep, so that is the right function. And so in Desmos here, what we'll note is if I turn off that green function, it's overlapping with the blue one, which means that Desmos agrees that my simplified version of that function is the same as what they would say is p prime of x. So that's good. Pretty happy with that, and we can keep going. So I had to pick this up, so let's do that, and that is the end of this section. So that was another 9 points. So we're currently, I guess, 29 points into the exam. Next up, compute these limits, show your work. In particular, if a limit does not exist, briefly explain why. All right, so the first one is 3a. So the limit as theta approaches pi over 2 of 1 minus sine theta over 1 plus cosine 2 theta. So one of the things is if this is ends up being defined at this point, and it doesn't give us that 0 over 0 type of expression, then we can probably say really quickly what's going on. So this is going to be 1 minus the sine of pi over 2, so it's 1 minus 1 in the numerator, so that's approaching 0, over 1 plus the cosine of pi over 2, which is cosine of pi over 2 times 2, which is the cosine of pi. cosine of pi is -1, so it's 1 plus -1. That approaches 0 as well. Okay, so it approaches 0 over 0. What that means is indeterminate. It means it is an indeterminate form. Indeterminate form means we don't know exactly what's happening. It doesn't mean that it doesn't exist. There's a chance that it still might not, but it could be any kind of combination of situations here coming up. Now, especially in, well, do you know what? I'm almost tempted to use a trig derivative and then cancel some stuff out that way. Or not trig derivative, trig identity. I'm pretty sure that, I think it's cos squared x minus sine squared x is the one that I would use. However, I'm just going to, because again, this is actually kind of funny because I'm a little bit on the rusty side, but at least I can remember some of the ways about how we would come up with that stuff to begin with. So cos 2 theta is cos, same thing as basically cos a plus b. And I know that that one is cos minus sine. And so it would be cos squared minus sine squared, which is what I thought. So that's good. All right. Next up, I'm going to do it that way this time. I could use L'Hopital's rule, and that would be probably my go-to most of the time. But let's see this thing work algebraically without taking a derivative here. So get 1 plus cos squared minus sine squared. So I'm going to put the 1 minus sine squared first, actually, plus cos squared. Ooh. Actually, so 1 minus sine squared x is the, and I could have chose the cos squared x minus, or 2 cos squared x minus 1 is probably the other one I could have chose, but that's okay. So it's going to be the same thing. This 1 minus sine squared x is cos squared x in the denominator. So I get the limit as theta approaches pi over 2 of 1 minus sine x over cos squared x. Now, what ends up happening here is now I can see that the denominator of this function, I guess, is going to be 0 squared. So, still 0, 0 in this case. Well, that didn't do anything, did it? All right, so I guess I'll just go to L'Hopital's rule now. I thought I was going to be able to do something a little more with factoring, but obviously I haven't got it set up that way. Oh, do you know what? Yeah, I'm going to keep going. I'm going to multiply by the conjugate now. So multiplying by the conjugate, top and bottom, is going to give me, in the numerator, 1 minus sine squared x, or sine squared theta, which is the same thing as cos squared theta. So I'm going to write that down. So that's cos squared theta. We already have the cos squared theta in the denominator, so that's going to cancel, and we're going to be left with 1 plus sine theta. And so sine of excuse me, sine of pi over 2 is 1. So this is 1 over 2. So it looks like this is going to approach a value of 1/2. Now, just not that you have to do it this way, but just as to see what it would look like with L'Hopital's rule instead, we would have here the limit as theta approaches pi over 2 of derivative of the top, which is going to be negative cosine theta, over the derivative of the bottom. 1 is 0, and then you get the cosine, which gives you negative sine. Leave the inside alone, times the derivative of the inside, which is a 2. And so we would end up here with, in this case, cosine of pi over 2, which ends up giving you 0 over, so it ends up giving you 0 over 0 still right now. So you got to go another step. So that's not any better, is it? Pi over 2, and then you'd have the derivative of negative cosine is going to be positive sine, and the derivative in the denominator there is going to end up being negative cosine of, kicks out another 2, so it's 4. So you would end up getting the limit as theta approaches pi over 2 of 1 over, well, don't need the limit anymore, 1 over, and then it's negative cosine of pi, which is going to give, so it's positive 1/4. So what did I do here? That so 1 minus sine theta, that's fine. 1 minus sine theta plus, that's fine. So that's cos squared. Oh. I lost this little bit. So this is actually 2 cos squared. I'm not going to back that up and fix it. I'm just going to leave it the way that it is. My apologies for that first time. So that is actually, I lost this one, that term. So added together with the cos squared that's already there, you get 2 cos squared. So then everything's the same except for this is a 2 down here. As well, and so I have an extra 2 multiplying here, which gives me 1/4, so I can get a quarter both ways. I'm surprised the L'Hopital's rule ended up being a double application, so it was no better. All right, next up, I'm going to do 3b, and so for 3b, we get the limit as x approaches 0 of 3 to the x minus 1 over 2 to the x minus 1. So in this this particular case, I do get basically what ends up being 1 minus 1 over 1 minus 1. So what I'm going to do instead is take the derivative top and bottom. So you get 0 over 0, so you can use L'Hopital's rule. So it's going to be the limit as x approaches 0 of 3 to the x ln 3 minus 0 over 2 to the x ln 2 minus 0. Now this is a 1 and a 1, so you end up getting ln 3 divided by ln 2 as the limit there. All right, next up, we get 3c, which is the limit as t approaches 0 of t minus 3 over t squared minus 3. All right, so in this particular case, put in the 0, and you get minus 3 over minus 3, which is 1. So this thing is a continuous function at 0, continuous function at 0. And so you end up just getting nice normal values divided by each other at that particular point. So sometimes they pull that little trick as well. All right, so I think that is the end of question 3. It is. I think those all had existing limits, so that's kind of interesting. I mean, I could. Again, if you're checking questions on your own and you're a little bit interested in how things are turning out, Desmos is really, really good for checking these types of things. So for limits, all we got to do is see how the function behaves around that spot. So that's 1 minus sine x divided by 1 plus cos 2x. And we're specifically interested in where this kind of behaves at pi over 2. So pi over 2 is looking like right there. So that's at a quarter. It's a minimum, and that is what we found. So that's good. The other ones I'm pretty happy about. So that was the only one I wasn't entirely sure, and I made the mistake earlier by not adding the cosine in. So I figured it wouldn't hurt to do a quick check there. All right. So next up, we are going to number 4. Okay, so we've done a lot of the, well, probably basic stuff. This one says, find an equation for the line tangent to the curve defined implicitly by the relation, so this is question 4, 6x squared plus 3xy plus 2y squared plus 17y is equal to 6. Okay, let's go. So this is done implicitly, so taking x derivatives everywhere. First part is just going to give us 12x. Next part is going to give us 3y plus 3xy prime. It's a product rule, so I took the derivative of the x first, took the derivative of the y second, plus 4y prime. So the 2 comes down, leave the inside alone, times the derivative of the inside gives you that y prime, plus 17y prime is equal to 0. So I have y prime in 3 locations. I'm going to take those 3 spots, factor out the y prime. It's going to leave me with 3x plus 4y plus 17. I'll divide that over onto the other side, which I'm going to have on the other side negative 12x minus 3y when I bring that over. Factoring out the y prime and then dividing it over, you get 3x, as we said, plus 4y plus 17. All right, so that I think is our derivative here, and we are looking specifically for the line that is tangent to this this wonderful function at that particular value the particular value of -1 comma 0. So we know that that's a point on it. That's helpful. We also know that the slope is this, which at this particular location is going to be -12 times -1 minus 0 over 3 times -1 plus 0 plus 17. All right, so that would be 12 over 14 maybe? It's equal to 6 over 7. Okay, so that's our slope. And then I'm just going to say that the line, it doesn't tell us what form the line has to be in. So I'm just going to do slope point form. So y minus y1 is equal to m times x minus x1. So in this case, y minus, the y value was 0, I believe, is equal to 6/7 x minus -1, I believe was. So x plus 1 there. All right, so I'm going to graph both those two. Of course, you can't do this on an exam, but I'm just doing it to check so that when you go to do your solutions, that you either know how to do it yourself or you are a little more confident in the values that I'm giving you. So 6x squared plus 3xy plus 2y squared plus 17y is equal to 6. Now let's see what beautiful thing this gives. Ooh, it's actually just a rotated ellipse. That's kind of nice. All right, and then we are going to plot our point that we got, which was y is equal to 6/7 of x plus 1, maybe? All right, pretty sure that was the case. I'll just double check, although the picture looks good, so I'm hoping it is. Y is equal to 6/7 x plus 1. And so right up here, at the point -1 comma 0, we get a really nice line that is the tangent line at that point. So it looks like we were successful. So that one was actually worth 8 points. We did that one quite quickly compared to some of the other ones that were worth even less than that. So the work there was just the implicit derivative, plugging it in, and then a very quick writing down of that linear equation. All right, next up, question 5. Evaluate the expression tan of the inverse cosine of x. Ha! That's funny, because I had to do something like this just a little bit ago when I was dealing with this sort of thing. So I'm going to say that so tan of the inverse cosine of x. So I'm going to say let y equal inverse cosine of x, which means that the cosine of y is equal to x. So if I draw a little diagram, and y is our angle, so y is our angle down here, then the cosine of this angle, which is adjacent over hypotenuse, is supposed to give us x. So the easiest ratio for that is probably x divided by 1. And then if I want to, I can label this side over here as being this thing squared plus that thing squared is equal to that thing squared, or in reverse, that thing squared minus that thing squared. Square rooted is this one. So that's what we get. What we actually want is the tan of y. So tan of y is tan of y in our diagram. So opposite over adjacent. So the expression we're looking for in the end is the square root of 1 plus x squared over x. Now, that's not an awful question, but specifically, you probably have to remember some of the derivation of the inverse trig derivatives in order to know how to deal with that. Or you were really comfortable during some of the stuff that you covered maybe during pre-Cal A, but probably not. Probably didn't. I don't know. It's up, maybe up to who was showing you that stuff. All right. So that is 5. 6. Just to let you know, that's worth 2 points on a 100-point exam, and to get your A+ or whatever, it's 90 marks or above. So it's if you were feeling like, oh, I don't know if that one's reasonable, you can toss it and make a couple more mistakes and you're still okay. All right, so question 6. If your goal is an A+, and if your goal is something else, then you got even more flexibility there. So suppose f is continuous on the closed interval 1 to 5. So, whoops. And then we have f is continuous on that. And differentiable on the open interval. Oh, this sounds a lot like some of our theorems that we have stated. It tells us that f of 1 is equal to 8, and f of 5 is equal to 4, and f prime at 3 is equal to 1. Answer each of the following, justify your answers. Does f prime of x equal -1 for some x in the open interval between 1 and 5? All right, so first of all, I'm going to do a little picture-ish of this stuff here, which at 1 we're at 8, 5 we're at 4, and then we know that the slope at 3 is actually some sort of positive 1 there. So it could have been negative before that, so it could be down here, but it's something like this, somewhere along this. All right, so does the slope have to be -1 at some point? The answer is Yes, but we can show it a little more directly by using mean value theorem. So mean value theorem says if a function is continuous on the closed interval and differentiable on the open interval, then it is true that there exists some c such that f prime of c is equal to basically the slope between the two endpoints. And since we know the x values and the y values for those endpoints, we would have delta y, delta x. So you would get -4/4. So according to mean value theorem, MVT, there does exist maybe a C between 1 and 5 where f prime at C is equal to -1. All right, does f prime at x equals 0 okay, so the answer to that is that this was an increasing function at one point in time, but because it becomes in the end a value that's lower than what we had to begin with, that means that there is a local max that occurs that is not at or a local min beforehand. I guess we could have gone like down like this and gone like that, or you could go up like this and then kind of down. However, there has to be that slope of +1 somewhere in there. And for that to happen, in order for you to come down and then go back up, if you have a negative slope to begin with, then you have a positive slope after that. There has to be a slope of 0 somewhere in in that interval. If you instead go up to begin with, in order to come back down, you need to have a local maximum happening somewhere over in this area here. It's actually, yeah, so the only thing is, in order to connect these two, it doesn't really matter what you do beforehand. Once you get, if you've gone down too far below, I guess. Anyways, so justification for this one. The answer is yes. So we've shown. Okay, so we have shown that the. Does it say that the derivative is? It doesn't. We've shown that the derivative is -1, guaranteed at some spot, and it's +1 at another spot. So if it's differentiable on the, I'm trying to think, if it's differentiable on that interval, it means there's a value at each point. Continuous. I'm trying to think of whether it being continuous if it's differentiable, if that means that the derivative that it's smooth. It does for the original. So I think that means that you could do intermediate value theorem for the derivative and say that since you have a -1 and a +1 for your derivative, according to the intermediate value theorem, because the derivative is a continuous function, then there has to exist a place in between those two where the derivative is 0. Wherever that ends up being, it doesn't matter because it's somewhere on the interval between 1 and 5. I think that's okay for that one. Could f of x be greater than 8? No, could, for some x in 1 to 5. So could it have gone up to begin with? Yes. Yeah, we kind of talked about that a little bit. According to everything that's been stated so far, we could go up to begin with, and we'd have values that are greater than 8. And as long as we have a slope of 1 when we go through 3, then you could take a sharp downturn, and that would be fine. So can it be graded? Could it? Yes. Does f have an absolute minimum on 1 to 5? Yeah, it's a continuous function, so all continuous functions have absolute maximums and minimums. So it's guaranteed that it will have some minimum value. It's called extreme value theorem. So since it's continuous on that interval, then there is a greatest possible value and a least possible value for that function there. So I guess I didn't write much for that last stuff. I mostly just said it out loud, but that's kind of what I would end up putting down for that material. So 7, sand falls from a conveyor belt on top of a cone-shaped pile. Yeah, I gave you something like this, I think. The height of the pile is always 3/8 the base diameter. This is very similar. So let's see here. The height is 3/8 of the base diameter. How fast is the radius of the base of the pile increasing, and the pile is 4 meters high? So the h is equal to 3/8 2r. So h is equal to 6/8, which is 3/4 r. Might use that in a second. We know that the volume of the cone is 1/3 pi r squared h. All right, so we can get this. We have the rate of change of volume. That's the 10 meters cubed per minute. So they gave us that in the question. So dV by dt, the sand is falling onto the top of the cone pile, and it will grow the cone pile. So it's increasing its volume at a positive rate of 10 cubic meters per minute. So I know dV by dt, and in the end I want to know dr by dt specifically. So dr by dt when the radius, pile is 4 meters high, so h is 4. All right, so v is equal to 1/3 pi r squared, and then I'm going to put in 3/4 r for the h value, because then my equation is made up only of things that have either the rate I want to know, which is r, or the rate I already know, which is the rate that v changes. So 3 cancels out with a 3 there. We get pi r cubed over 4, I think. And then I'll take the derivative of both sides with respect to time. So dV by dt is equal to pi over 4 3r squared dr by dt. So what we want to know is specifically what the value of this is when h is 4. So I need to know what r is when h is 4. So let's back up to this little thing right here, which says that h is equal to 3/4 times r. So if I took the 3/4, multiplied it, or moved it across, so it's 4h over 3. That would be 4 times the height of 4 over 3 is equal to r. So that would be 16/3. So that r value is 16/3. So we get dv by dt is equal to pi over 4 times 3 times 16/3 squared. Actually, so that's 10 plus 10. 4 moved up, 3 and pi down bottom, 256 down bottom for 16 squared. I don't know if they do that, but specifically when the height is equal to 4 meters. Meters, I think it was. Yeah, meters. Yeah. So I don't know. Cancel some things out a little bit here. So it's 3 over 64 pi. I'm going to just do a quick double check here. So the height is equal to 3/8 the base diameter. So 2r for d, so 3/4 the r. That seems fine. 1/3 pi r squared h. That looks good. So 3/4 r. Cancel the 3's and we get pi r cubed over 4. That looks fine. So the derivative of that is pi over 4. The 3 comes down. R squared times the derivative of the inside, which is dr by dt. That seems okay. If the height is 4, then it's 16 over 3. For the radius, 16 over 3 squared. Yeah, I guess so. Seems okay, but numbers are a little bit funny. I thought it was it's a little smaller, and I thought it would make most sense probably to list in centimeters, but this is in meters per minute. So centimeters, you just multiply by 100, and so the ratio would end up being a lot nicer looking, I guess. In term, not nicer looking, but it is a decimal form, would look nicer. All right, I think that one's okay. Next up, question 8. Find and justify with limits all vertical or horizontal asymptotes, if any, for the graph y is equal to x minus 3x squared over x squared minus 4. All right, so the limit as x approaches infinity of y is equal to, it's the ratio of the highest power. So in this case, it's -3 over 1 because it's the same top and bottom, which means, and that we could do it with the negatives too, if you really wanted to be clear that this doesn't have a different one when you do that. It's squared, so it doesn't matter. But so therefore, there is a horizontal asymptote at y is equal to -3. And then for the vertical asymptotes, those are just going to be discontinuities in the denominator, as long as they are not paired with the discontinuity in the numerator to make a POD instead, which the numerator factors into x x times 1 minus 3x. So neither of those are going to have the same factors as the denominator, which are x plus 2 and x minus 2. So that's good. So we basically want to show that the limit as x approaches 2 of from the right, I guess we'll do. And then, so I'll do one-side limits from them. So I guess if all we're supposed to do is show that there is a vertical asymptote, I probably only need to do it from one side. If I wanted to show what it's approaching as you get close to that vertical asymptote, I show from both sides. But maybe I'll just do it from one side, just to in the interest of time. So that's just a factored version of what we have up top. So what I'm going to do here is I'm going to approach 2 from the right. So if I do that, I am going to get basically nice normal numbers here that are going to be like positive and negative. So it would be 2 and like negative 5-ish for that second one. Down here, I'm going to get 4, which is positive. But this one's sketchy. So this is the number that is very extremely small. So it is small, but positive. So if you multiply that out, it's going to be extremely small, positive number. So if you take something that's a normal size negative, so it's actually really close to negative 10-ish, and then you take it and divide it by a very, very, very increasingly small positive number, that's going to blow up, and it is going to make an extremely large negative number, and that's the behavior that happens around a vertical asymptote. So we have a vertical asymptote at x is equal to positive 2, and we could do the same thing here for negative 2. So the limit as x approaches negative 2, doesn't matter from the right or the left, we'll do the right again. And so for the negative 2, that was like a negative 4. This one's like a 0. It's going to be from positive side again, because it's going to be approaching from the right. So it's like negative 1.99999. Add that together, you get a very, very small positive again. So small positive. And up top, we're going to have a negative with a positive. So it's a negative again. And so you're going to end up having I don't know what I'm doing. Vertical asymptote at x is equal to minus 2. All right, so you can show it with limits. You probably could use a little bit different reasoning if you wanted to there as well. I'll do that graph real quick because it's not a long one to do Desmos there. X minus 3x squared. That was a fun one. So x minus 3x squared. Oh. There we go. Over x squared minus 4. Right, I gotta. So there's the coming in from the, oh, right. What did I do wrong with that thing? I mean, it's still the right result there, but that's not the right sign. Let's see here. So negative value. Oh, positive. Oh, that was a negative. Sorry. So it's multiplied by the negative that's already down there. So, and so it would end up giving you a very, very large positive value coming in on that side. Again, that wasn't really that important for showing where the vertical asymptote was, but it should be right anyway. All right. for B, it says on a set of axes indicate the asymptotes and sketch a possible graph. Oh, I cheated. So it's basically saying do a really quick, because of the asymptotes, do a really quick example of what this thing could look like. So -3, so it's got to follow along that. And then at -2, +2, you got stuff like that. So you're probably looking at, it's got to follow along those. It's going to have intercepts at 0 and like I got it actually. So x 1 minus 3x. So it's at +1/3. So there's another intercept somewhere over here. So you're probably looking at like that. And, well, except for not quite as butchered there. I'm not good at this game. Let's try it one more time. Something along those lines. All right, so, yeah. Which, if we compare against it here, seems fine. It almost doesn't look like it has the second one. It dips so little below that that axis. It looked like there's only one x-intercept at the normal zoom there. All right. So next up, find a function f satisfying f prime is equal to sine pi x over 4 plus 1. Oh. This is kind of unfortunate, and depending on the year, sometimes they put this on the 1003 and sometimes they don't. This year they did for the 2010. I'm gonna choose for now to skip 9 and 10. So the reason I'm skipping 9 and 10 is because they are introductory integration topics. So the first one, you're looking for an antiderivative of 9, which you know enough to be able to do that. You're looking for something that gives you an answer that is what's written here. So you would need probably some sort of cosine function in order to get the sine to kick around there. And if you see the 1 over x, you might know that that's ln x to begin with. So you probably can do that, but we didn't cover it together, so I'm not going to bother doing that right now. The same thing with question 10, find the area underneath of that parabola. That is also using, oh goodness, a little bit of integration. All right, so the next one here, throughout this question, f is defined as being f of x, so this is number 11 now, is equal to 3x to the 4 minus 8x to the 3 plus 6x squared plus 1. And it says verify by differentiating and factoring that, oh, okay, so it gives you the first and second derivatives, but it wants you to show that it's true. So we are going to do this ourselves, I guess. So this is 12x to the 3 minus 24x squared plus 12x plus 0. We can factor out a 12 and an x here, so we'll do that. So 12x, and that leaves us with just x squared minus 2x plus 1. And that actually is a perfect square factoring, so it will go x minus 1 all squared. So it gives you x squared minus x times minus 1 is give minus x, and then another x times minus 1 is minus 2x, and then plus 1 at the end. So that's that, and that's good according to what we have there. And our second derivative, I'm actually going to do the second derivative by looking up at this line because it's the simplest version in terms of taking the derivative. So that is going to be 36x squared minus 48x plus 12. which gives us, in this case, divide everything by 12. You're going to get, divide everything by 12. We have to factor it up front. And that's going to be 3x squared minus 4x plus 1. Okay, isn't cheating. They do factor this. It's kind of awkward because once you know the factoring, you don't really have to show anything to do the factoring. You factor by guess and testing. So it's 3x and 1, and then 1 and 1, and then you just got to get your signs right. So it's either both positive or both negative. It's obviously both negative because of the middle term. So you double check. 3x times negative 1 plus x times negative 1 is negative 4x. That's great. Beginning one, positive 3x squared, and final one, positive 1. So that's fine. Determine the intervals on which f is increasing or decreasing. So we would need this thing. So that's 12x. I guess I can look here. So f prime of x is equal to 12x. So increasing or decreasing, basically according to Fermat's theorem, it either happens at DNEs or zeros for your first derivative. I believe it's Fermat's theorem. Can't remember off the top of my head apparently. All right, so we get a 0 and then plus 1 twice. So what we do is we test on these intervals if we're thinking first derivative test. So if I put a negative 1 into this, it's negative, and then squares, so it's negative. If I put a half into this, then it's positive, and then it squares, so it doesn't matter, so it's positive. And same thing on the other side. If I put a larger value into that, it squares, so it's positive, and that's positive too. So we get that this function, f of x, is increasing on 0 to, now this is, it's going to go up, flatten out, and keep increasing. I think that it's okay to say that it goes from 0 to infinity. If you think because it levels out there and then grows afterwards that it's 0 to 1 in union with 1 to infinity, I think that's probably okay. But if you can continually grow while going through 0, so I think it's increasing. All right, so f of x is decreasing on negative infinity to 0. All right, find a local maximum and minimum value. So there's a local minimum at 0 comma something. So local min at 0 comma, and that would be, I gotta look at the original, oh, I guess I have it on my paper. So the original function, if I put a 0 into it, it's y-intercepts 1. So there we go. Determine the intervals on which f is concave up or concave down. So we have the second derivative as well. So second derivative, this is part D, is 12x minus 1, 3x minus 1. So what we have here is that we do the number line thing again, positive 1, and then 1/3 for that other one. Okay, so doing our tests values, if we put in a 0, it's a negative times a negative is a positive. If we put in half, so that would be a negative times a positive, so it's a negative. If we put in a value like 10, then that's definitely positive on the other end. So it does have, it's concave up, f of x, I should be careful here, f of x is concave up on negative infinity to 1/3, as well as 1 to infinity, and then f of x is concave down on 1/3 to 1. All right. Again, that's the end of that one. But let's do a quick little look-see at that particular function. So I'm going to put in I'm not good at this game. All right, so you're flying everywhere. Oh, I'm gonna bump in my hair. F of x is equal to, now where is that thing? 3x to the 4 minus 8x to the 3 plus 6x squared plus 1. All right, so important things that we said. Said that there's a local minimum that would occur at 0, 1, so that looks fine. We said that there were changes in concavity that happened at 1/3 and 1. So this is concave up, switches to concave down, switches to concave up. So that does look good. I guess that's all we had to figure out. So it looks pretty reasonable. So sorry, I think I had my cursor on my screen that you can't see. So this is our local minimum. That's good. That was at 0, 1. And then this is all concave up. Looks like it switches somewhere around here, which we said it happened at 1/3. That seems pretty reasonable. And then here it's concave down, so this is an unhappy face type curve. And then it switches here at 1 to become concave up. So seems great. Good. Okay, so that was graphing. That was page 6. Now I need page 7. That's 2. Oh, so it says to neatly sketch. It gives you grid paper for the function. So again, I use Desmos, which is a bit of a cheat because I've seen it already. We knew that it has a local minimum at 0, 1, and then I think that's what we found, right? I gotta go back to it. My memory's really good. So we found a local min there, yeah. And then we have that funky non-min or max at 1, which we know is an inflection point. And it's concave, what to start with? Concave up, so happy face. So happy face, and then we switch to a sad face, and then we switch to a happy face. And so this switch happens, there's an inflection point at 1/3, comma, and then we can put the 1/3 back in if we want it. And then at here, there's another inflection point at 1, comma, and we could figure out what that y value was. And we'd have to put those into the original function, we'd figure out what they were, and then we'd be able to graph it so that it looks appropriate. I think there's just one question left. So this one, so we skipped a couple, so we're a little short, I guess, time-wise. I'm about an hour and 19 minutes out of my almost 3 hours so far. So we're doing okay, even though we're chatting about things as we go. So 13, the space within a racetrack of length 2 kilometers is to consist of a rectangle with a semicircular area at each end. To what dimension should the track be built to maximize the area of the rectangle? Maximum rectangle area. Justify why there is a maximum. So, since it's semicircular, I'm going to justify to begin with. Since it's semicircular, if you make this thing the rectangle, sorry, if you make that rectangle too tall this way, then you're going to need a lot of the 2 kilometer long track on the semicircular part, which you're going to run out of track if you make it too tall. However, if it's not tall, then your area is not real big either. So you can see how this is going to get limited by, you want to make it tall so that you can get some area, but you can't make it too tall or else you take all the width away from the rectangle because it has to go into those semicircles. We can't just get rid of these. That's not part of the question. So we have to have it be that semicircular shape on the ends. All right, so that makes sense as to why you wouldn't just be able to make the rectangle be the only thing. I guess even if it were the only thing, it'd still be a max because you only have 2 kilometers of track. So let's go ahead and set up some variables in here. So if we said that I don't know, this thing is x, this is y, which means that the radius is equal to y divided by 2, because y is the diameter. It goes from one side of the semicircle to the other. So in total, there's actually 1 circle, and there is the rectangle in the middle. What we do know is that x on the bottom plus a circle worth of track, which is 2 pi r for the circumference, plus another x would be the entire way around, and that's only allowed to be 2 kilometers. So we would get 2x plus 2 pi y over 2 is equal to 2, or 2x plus y, or pi y is equal to 2. The area of the rectangle is just xy. We want to minimize that. But for an optimization problem, it has to be written in terms of a single variable. So we can write x in terms of y or y in terms of x. It doesn't really matter which is which. I'm going to write, I'm going to move the y over. So it's equal to 2 minus pi y, and then divide both sides by 2. So you're going to get that x is equal to 2 minus pi y over 2. All right, so that means that a is equal to 2 minus pi y over 2 times y, which means that the area, this is just the rectangle part of the area, of course. That's why we start out with the x and the y. So that is going to be, well, it's 2 divided by 2 times y, so it's actually 1 times y. And then the next part is going to be minus y, pi y squared over 2. Oops, I don't know why it's put an equals there. Just minus. All right, that looks good. We're going to take the derivative of that, set it equal to 0. So derivative with respect to the variable it's written in. So that's 1 minus 2 pi y over 2 is equal to 0, because we're maximizing. So that's going to be negative pi y is equal to negative 1, or y is equal to 1 over pi So if your y value is 1 over pi, apparently this is going to be a maximum area. Now, what are we looking for in the end? It says what dimension should the track be built. So the rectangle should be 1 over pi by, and then we have a relation for the x and the y. So it's 1 over pi times pi is actually equal to 1. So it's 2 minus 1 is 1 over 2, so it's half for the x. 1 over pi by a half. I don't think you need to put this, but radius of semicircles is equal to, and it's just half of y, so it ends up being 1 over 2 pi. So there we go. Other than a couple different integration questions, that is the extent of this particular final exam, and so that gives you an idea of what you might be up against at the end of a first year course. Hope you enjoyed. Take care.